So whenever we have exponential graphs and exponential functions, okay, what I want you to do, whether you're dealing with Desmos or you're dealing with the graphing calculator, is first off you have the original function here of y is equal to a times b to the x minus h power and then plus k. It still deals with the same types of things that we did before. It still has x minus h, just like a quadratic did, just like a square root function did, just like a cube root function, just like an absolute value function did. You still have x minus h, and that is not going to change. It's just a matter of the type of function that it is. You still have a plus k, and you still have an a value. Now, the only difference between what you've seen before and what you have now is that with an exponential function, you have an extra variable right here in your b value. Okay? Your b value here with, we just change it colors, okay? A is still going to do the same thing that it did before. Okay, as far as making it vertically stretch, shrink, flip, all that jazz. Okay, your b value though, okay, for right now, and what if you look over on the side wall, everything as far as the parent function or the original function is y equal to 2 to the x power. Okay, all that means is if I go to y equals, clear that out, and if I just type in, I'm going to type in 2, and I'm going to hit the caret button, and then change this first. So 2 to the x power. Now, if you're dealing with Desmos, then all you have to do is here is just to start graphing. Everything is, you're just going to go y equals and then 2. Depending on what you have, if you want to have this here, you can put it up and then x. Okay, and it'll graph everything there. All we're doing whenever we have 2 to the x power is basically just what's making it exponential is we're just multiplying everything by 2 however many times, whatever our variable is. So whenever we go with my graph, and if I do it here, it's going to be the same, it's just not going to be zoomed in as much, which is fine. Okay, but if we notice, okay, here it's going to be the same as if it's in Desmos. If I look at my table, whenever I plug in values, what am I doing each time, or what, as far as my blue values, what's happening? If it's 2 to the first power, it's just 2. If it's 2 to the second power, it's 4. If it's 2 to the third power, it's 8. 2 times 2 times 2 gives me 8. If it's 2 to the fourth, it's 16. Basically, it is the part of my function whenever we have, or whenever we had our table, and we did this, and we had our a value here, and we had 1, 2, 3, 4, 5, so on and so forth, and we had a squared. And then we had a to the third. And then we had a to the fourth. And then we had a to the fifth. All that's happening is we're just basically taking that value, and whatever my base is, I have 2 to the second. That was just 1 straight across. 2 to the second power was 4. 2 to the third power was 8. 2 to the fourth power was 16. 2 to the fifth was 32. All we're doing is just basically staying in this row. If I would have 2 to the 6th, then I would have 64. If I would have 2 to the 7th, so on and so forth, 2 to the 8th, it would just keep building and keep growing. Okay? I would just be multiplying my base. If I would have the 3, it would be 3, it would be 9, then it would be 27, then it would be 81, so on and so forth. I'd just be going straight across as far as my values are concerned. Now, just like we did before, so it says, so if I'm going to change the value of A, so whenever it is bigger than 1. So all I'm going to do is I'm going to go to my y equals if I'm dealing with my function. I'm going to keep it in there, so if A is bigger than 1, so what is a number that's bigger than 1? What? 3? Okay. So I'm going to go 3, and I'm going to hit parentheses. I'm just going to write it just like it was here. I'm going to have 3. My A value is 3. And then I'm going to have 2 to the x power. So if the blue one was my original, the red one is my new one, what happens? If A, what?
It's like a shrink or a stretch.
It's going to be a stretch. Okay? Because what was A? Whenever I multiply, whenever A was bigger than 1 before, what was it? It was a vertical stretch. So that means all I'm going to do here, so if A is bigger than 1, then what am I going to fill in on this line? So then my graph will have a vertical stretch by factor A, whatever that A value is. So like since we used 3, it would have been a scale factor of 3. If we were going to use a 4, it would have been by a scale factor of 4. If it was a 2, it would just be doubling it up. It would be a scale factor of 2. It doesn't change what we've done in the past. A is still A, it's just we have an actual base that we're going to work with. So then what do you think is going to happen if I have a value? Okay, so if I go back and I have a value that's between 0 and 1. So what kind of number do I need if it's going to be a value between 0 and 1? A fraction. So instead of having 3 times 2 to the x power, what number do you want to have in front? Okay. So I'm going to go 1/2. I'm going to put it in parentheses. And then I'm going to take the 2 to the x power. So now this is the black line. Notice that they're still going along the same, but now it's not moving up as fast. It's got to go further to the right before it starts to climb. So then what did I do? Even if I go with Desmos, and if I have a second line, so we had 3 times 2 to the x power, so there's the blue one. Now for my second one, I'm going to have 3 equals. I'm going to do 1/2 times 2 to the x power. So there's my green one. Notice that I have all of these values. For each one, whenever x is 0, it's a difference of 1 is a scale factor of 3. It should be hopefully pretty simple. if you notice, everywhere that I go, if I have a point at 2, 2, as far as my green one, that's half. So what's half of, whenever x is 4 here, or 2, excuse me, my y value is 4. Notice that the green one is always going to be half of whatever my red one is. Same way, if I'm up here at 212, the blue one is always going to be 3 times my original. Does that make sense? So then if A is between 0 and 1, then what's going to how is that going to affect my graph? Then what? My graph will what? Have a vertical shrink. By a factor of A, whatever that is, whether it be 1/2, 1/4, 1/3. Same thing. So it says, again, we have the, and I'll write it again just so you know what we're working with. If we have y equal to a times b to the x minus h power plus k, if it's x minus h up top, so if it's x minus h, what do you think it's going to do to my original graph? If I have my original graph of y equal to 2x, how is it going to transform or move or adjust my new function? Is it going to go left? Is it going to go right? Is it going to be a vertical shrink, stretch, up, down? What's going to happen to it if I'm going to subtract h? What's happened to it if it would have been before, whenever we had x minus h squared? What did it do if it was a minus h? Which way did it affect the graph? It took it right, that value, right? Correct? So then what's it going to do? How's it going to move my graph? It's going to move it right h values, okay, whatever that is. So in terms of seeing it, if we either put it in the graphing calculator, if I get rid of my two other ones, and if I have 2 to the x, and I have 2 to the x minus 6, and I hit graph, the blue one is still the original. Okay, it's still going to go through the original values. All that's going to happen, now the biggest thing here is what students want to say is that, well, it is a vertical shrink. Okay? It's not a vertical shrink, it's a horizontal shift. Okay, we shifted it 6 units in this case to the right. Okay, because we didn't change anything. If we just look at our table, okay, and it's easier with obviously here, is that we still have some of the same values. Notice that if we have a value up here at -5, in blue we have the same value as we do down here in red. Well, how many different, we didn't change the values. Okay, we just moved the values. So it's just a matter of, if we're at negative 5, how many steps did it take for us to get down here to a positive 1? 6 to the right. Same way with negative 4. How many values did it take to get us to, if we had, like what's in blue, that this number matches this number here. Same way that 1/2 matches down here. What did we do? Well, we had to move it 6 to the right before we could get there. Just because it looks like it's smaller, all it did was shift. Okay, it didn't shrink, it didn't stretch because our values didn't change. Okay, we didn't multiply anything, we just moved our values one way or the other. Same way if we would make it x plus h, so if we would go x plus 6 instead of x minus 6, so if we would take the same value and we would have 2, we would take it to the x plus 6 and we graph it. Now which way did we move it? Moved it left 6. Again, it's just a matter of finding values and how the actual number didn't change. The only thing that changed, so we had a 16 here from the original. Again, we're just going in that direction. Okay, we had to move back to the left 6 spaces. Same way with the 8. From the 3 to the negative 3, we would have to move back 6 spaces to the left. So then if we have x plus h, how's that going to affect our graph? It's going to move our graph left, h number of spaces or h number of steps, whatever that value is. If I still have y equal to what happens whenever k is positive? How is it going to affect the graph? How has it affected every other function up until this point? What has it done? Just move it left, right, up, down, sideways, flip it, dance, what? Yeah, so if it's positive, what's it going to do? So it's going to move my graph it's going to move it up k number of values. What happens if it's negative? It's going to move it down. Okay? What has happened with A, H, and K hasn't changed. Only thing that's changed for any of these is the type of function. What A, H, and K do still do the same thing. It's just a matter of the type of function that I have. Now, what's going to happen whenever a is negative? So again, same thing. Y is equal to a times b to the x minus h power plus k. So if a is negative, what do you think? What's what's happened before whenever our a value is negative, if there's a negative in front of my entire function? Flips it over the x-axis, right? So it's going to flip it over the x-axis just like it's done a million times before this. So even if I have the same type of function, and if I have y equal to 2x, 2 to the x power, excuse me, even if it's as simple as just putting a negative in front of it, I am going to have the blue one that's going to go up, and I'm going to have the red one that's going to go down. Everything's going to match. Okay? It's just one's going to be reflected over the x-axis. Now, the tricky one is really the last one. Everything up until this point really shouldn't be anything new because it's not. The only thing that's different is the type of function that we're dealing with. Okay? It's just now we're dealing with an exponential instead of a quadratic or instead of a square root or any sort of radical function or things like that. So now the question is, at the very end, what if x is negative? So what if it's y equal to 2 to the negative x power? So if I have my original of y equal to 2 to the x power, so now I still have a 2, but it's instead of it being a negative out in front, it's a negative up top. The blue one still is what it is. What happens to the red one, though? What does it do? What? It flips over the y-axis. Okay? It basically, what it's going to do, and what we'll talk about tomorrow, it turns it from an exponential growth problem, like the one in blue, to exponential decay. It goes from the plane taking off and going into the sky versus the plane coming out of the sky and landing on the ground. So all it's going to do whenever we have a negative up in my exponent is it will flip over the y-axis.